Hey guys, we're continuing in our chapter 10, and I literally hit record and I forgot I'm going to need my answer key. Oh, it's right here. Never mind. I also have a little classical music going on in the background because, can only help our learning, right? Oh, that's a little loud. That's okay. So as we move into rotation, we're going to talk about rotation that has angular acceleration that is constant, meaning like it's constant. Like if it's accelerating at 2, it's going to continue to accelerate at 2. So acceleration is a number. It's not like a variable equation. So something we need to kind of reference is we need to go back to chapter 2. Let's talk about some of our favorite linear equations. We're going to talk about 1, 2, 3, 4, 5 of them. So maybe we would kind of want to, all you perfectionists, go get yourself a ruler. Okay. Divvy this up into 5 equal sections. Okay. Here we go. So the first old linear equation that I want to talk to you about is when we were looking for velocity of something. The velocity of an object at any time can be found by the original velocity plus the linear acceleration plus the time that has expired. The missing variable was we had no idea what the change in distance was. Or if you don't like using delta x, you could just say x minus xo. Those are equivalent. Okay. Now let's talk about our second one. The second one we talked about was our position at any point in time could be found by taking our original position, adding, I'm going to move that over to, I don't like that one, so we're going to, well, there's 2 ways we could write this formula. We could do x minus xo, like that, equals original velocity times time, plus 1/2 acceleration times squared. If any of you want, because this is delta x technically, you could just take this guy to the other side if you wanted to. So that was the second one. The missing variable we did not know was the final velocity of that particular time period. All right, feel free if I'm going too slow to speed up the video. Okay, let's talk about the third one that we talked about and used a lot. The third one was that our final position could be found. Nope. Oh man, I did those 2 backwards. That's okay. No, I didn't. Okay. That our velocity squared at the end of a particular time period would equal our original velocity squared plus 2 times the linear acceleration times the change in position. So you could say x minus xo, or you could just put delta x inside of there. And the missing variable in this case that we were unaware of was the time. Let's talk about the fourth one. Oops. That's not too bad. So the fourth equation we used a lot, 1, 2, 3, 4, was when we wanted to find the final position, and or like any other variable inside of here, was the original position. Remember that could be transferred to the other side and just be made delta x, x minus xo, plus the velocity at that particular time frame times the time that has expired, minus 1/2 at squared. And the unknown variable was the beginning velocity. So this velocity that I'm pointing at was like the velocity at a certain time measurement. Like if it was increasing, like the new velocity, the ending velocity of that time frame. All right, last equation that we're going to make reference to, kind of old school here, is another one with position. Original position, remember you can take that over and make this side delta x, plus 1/2 original velocity plus final velocity times the time that had expired in that time frame. And what we didn't know in this particular one, we would have to know that it was accelerating, but we would not know the acceleration number. Okay, so what I'm going to do is, those are old school. now we're into rotational motion. So rotational motion is going to be incredibly similar to it, but we're changing like linear speed into angular speed. So let's say that we want to solve for our angular speed. Well, it would be our original angular speed plus the angular acceleration times the time period. And what I want you to see is like the complete resemblance of these two to one another. One is linear, one is rotational. The missing variable, just like it was before, is the change in angle. So delta theta, I'll put it over here since I put it over there. Delta theta, or if you don't like using delta theta, final theta minus original theta. Now let's talk about the second one and see the similarity to it over here. So we're talking about position now. So position in a circle is determined by your angle from the positive x-axis. So when we talk about position, we're talking about like theta, all right? So over here I had like final position minus original position. So over here I'm gonna have final theta minus original theta. Remember that could be replaced with change in theta equals the original angular velocity, right, kind of small here, times the time that has expired, or expired? Yeah, sure, whatever, plus 1/2 the angular acceleration times the time that has elapsed squared. Again, you can see hopefully the similarities, circular, linear. The missing variable in this case would be if we do not know our ending angular velocity of that particular time frame. I don't want to say the ending angular velocity overall because it's in a certain time frame. Okay, now let's move on to the next one. Again, very, very, very similar. So we take our ending angular velocity, sorry, that's a really bad angular velocity W, square it. That's going to equal our original angular velocity squared plus 2 times our angular acceleration times the final position minus the original position, or if you want to put in there, delta theta. What are we missing? Time. So we can solve for items. If we don't have time, we use this equation. All right, let's move on. Let's get a light on this thing. There we go. Helpful, who knows? Next, let's say that we want to solve for like position. Like where does it end? Where in the circle is it going to be? So we would do theta equals original theta. Please look at the similarity over here. It's probably going to be plus angular velocity, which it sure is, times time, minus 1/2 angular acceleration times squared. So it's all very, very, very similar to it. You just have to wrap your head around this is circular motion instead of motion in a straight line. So what don't we have in this particular item that we could still be successful without? The original angular velocity. Now, one more. We could also, oh, remember if you want to take this over to the other side, you could just write delta theta. Okay, one more like that. The final position could be found by taking the original position, adding 1/2 the quantity, the original angular velocity plus the ending angular velocity for our time frame times time. And what don't we know in this one? Angular velocity or acceleration. But we would have to know that it is accelerating either up or down. Usually in a circle, we're accelerating down because usually we give it some initial speed and then something makes it accelerate slower, like spinning a wheel on Wheel of Fortune. All right, let's do this thing. To throw a curveball, a pitcher gives a ball an initial angular speed of 36 radians per second. You know what, guys, would be really smart of us to write our units down somewhere. So give me a second. Maybe I'll get another piece of paper and you should too. I'm going to hit pause. All right. So these are our 4 main items that we need to like remember what kind of units they have. So let's talk first about angular velocity. Angular velocity we measure in radians per second. Okay. Now, angular acceleration is very similar. It's radians per second squared. Just like in linear, it was meters per second squared. Time is therefore in seconds. The only one that might be a little bit confusing, hopefully it's not too bad for you, is theta. Like, how do we measure our angles? We tend to measure our angles in radians. But just so you know, where did I write? I wrote a note on this page. Hold on. It's right here. I wrote myself a note. Let's go ahead and write this note on a formula sheet that you guys have. When trying to solve for revolutions, I'm just going to hold this here. This is just my work. I did the examples beforehand. Can you guys write this down? Maybe pause the video. When trying to solve for revolutions. Now, revolutions is how many times it's gone in a circle. Okay? So you're trying to say, like, how many revolutions did it take? Did it take 2 revolutions, 3, 1.5, blah, 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 blah. You're going to find theta. And theta will be found in terms of radians. So maybe you'll get 15 radians or 2 radians. After that, you're going to convert your radians to revolutions, knowing that 1 revolution is 2 radians. You can see I did an example up here. I was messing around with some examples, and I said, okay, if 1 revolution is 2 pi radians, I said, how many revolutions is 6.94 radians? Cross multiply, divide. Long story short, guys, you are going to you're going to pretty much just take your radians, divide by 2 pi, and if you need degrees, multiply by 360. So just kind of like a little helpful thing there, okay? All right, so hopefully you have that written down. Now let's go ahead and continue with example 1. So the picture is going to give it initial angular speed. I'm going to write this down, maybe right here. This is stuff that's given to me. Initial angular speed. And that's going to be 36 radians per second. I love that the units kind of give away what it is. When the catcher gloves the ball, 0.595 seconds later, its angular speed has decreased. So I know it's traveling in a straight line, but you just have to remember that the ball's spinning. Circle, 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 circle. So, but we're saying, like, as the ball goes through the air in this circular motion, it's getting a little bit slower as it goes through the glove. And it's saying that it's due to air resistance. Okay, that's great. We know that. We know that, like, things like friction can add and subtract speed and stuff. But they're just saying, hey, it decelerated is what they're saying, okay? I don't really care what made it decelerate. It's decelerating, okay? And this is its ending angular velocity. I find labeling things is the best way for me to keep my head organized around stuff. Okay, so that's just the given information. Now let's move to part A. Part A says, what is the ball's angular acceleration? Assuming that it's constant. Well, it's constant because that's what the title of the lesson is today. So guys, I have all these beautiful formulas up here that we're going to pay attention to. They're talking about rotational stuff. I don't have, let's see, what don't I have? I don't have change in theta. I have this, I have this, I have this. I need this, so I better not use this formula because I need it. So let's use this one up here. So final angular velocity equals original angular velocity plus angular acceleration times time that it happened. So final is 34.2. Original is 36. Angular acceleration is unknown. And time is 0.595. It would be absolutely wonderful if you guys could see the similarity of this section to chapter 2. I'm going to turn off my light because my calculator glows really funny when the light's on. So just some simple algebra here. 34.2 minus 36 divided by 5. I hit enter if you didn't see that. All right. So I have my angular acceleration equal to negative 3.025 radians per second squared. We're always going to put on our labels. There it is. That was a lovely answer. Very proud of ourselves. All right, now part B. How many revolutions? So if they ever ask you about revolutions, that means you really need to solve for theta. So theta is question mark. Okay, how many revolutions does the ball make before it's being caught? So we don't have theta, but we need it. So whatever equation we use needs to have a theta in it. Oh, P.S. We're assuming that the original theta is 0. Okay. So final theta. Let's do literally a ton of these, right? Let's pick. I don't care. You want to pick this one? No, because we have angular acceleration. I'm just going to pick this one if you guys don't care. I don't know why I'm drawn to this one. So what is our final theta? If our original theta is 0, so we're saying like, say at the beginning it's rotated 0 times. Okay. Original theta plus final angular velocity times time minus 1/2 angular acceleration times squared. And Mr. McBurney on his, he used, what did he use? He used this one up here. Okay, doesn't matter. I really hope not. Okay, we got to get 20.88 radians to start with. Okay, so final theta is 0 plus ending is 34.2 times time 595 minus 1/2. Angular acceleration is negative 3.025. Time is 0.595 squared. Let's go ahead and solve this thing out. Ready? So 0 plus 34.2 times 5 minus 5 times negative 3.25. All right, I'm doing this on the fly. I'm using a different equation than Mr. McBurney, but look at that, guys. It doesn't matter because we ended at the same thing. So yippee skippy. Don't care what formula you use. Please make sure you get 20.88. Now, this says 20.88, but remember theta is measured. It's not measured in revolutions. Theta is measured in radians. Well, that's okay. We can do this. To get to revolutions from radians, didn't I write this down? When trying to solve for revolutions, find theta in terms of radians, convert it knowing that 1 revolution is 2 pi radians. So all we need to do is take that and divide it by 2 pi. You can make a proportion and solve if you want, but if you divide this by 2 pi, which is 1 full circle, okay, because 2 pi is 360 degrees. If you divide that by 2 pi, so 20.88 divided by 2, oh, here, look how you have to divide by 2 pi. Put in parentheses, okay? And, oopsie, what did I do? Oh, I put parentheses there. 3.323 equals 3.323, and that's how many revolutions. If somebody was like, hey, how many degrees did it travel? You just take that answer and you multiply by 360, and that's how many degrees it traveled, because that would be 3 circles and 0.323 of a circle. Okay, all right, let's go to number 2. I really enjoy this because it's so similar to the stuff we did in chapter 2. Okay, it'd be amazing if you guys got, like, we were back at school and I gave you your chapter 2 tests back and stuff. You would probably be so proud of yourself because, like, it's just amazing how much you've grown. On a certain game show, contestants spin a wheel when it's their turn. One contestant gives the wheel an initial angular speed of 3.4 radians per second. So initial angular speed, right here, is 3.4, okay, initial angular speed. It then rotates through 1 1/4 revolutions. Ooh, let's write this down somewhere. So 1 1/4 revolutions. There's no formula that involves revolutions. You need to change that to a certain amount of radians. Okay? We need to figure out how many radians that is. Well, guys, I mean, I can show you like the proportion up here if you want. This will solve it all the time. We know that 1 revolution is equal to 2 pi radians. This is a mathematical fact. So if we have 1.25 revolutions and we're trying to figure out how many radians that is, we just cross multiply. So this would be like the x down here. So it would be 1x equals, you just multiply. 1.25 times 2 pi. So that would be 7.854. Okay? So you just have to multiply by 2 pi, which is exactly the inverse of what we did on the previous example when we divided by 2 pi. All right, so now that we have that, that is, let's see, it then rotates through, that would be the final theta, and we would consider the original theta to be 0. So maybe we want to kind of acknowledge this area as like the given information, and we could say that the original theta would therefore mean that it started at 0. Okay, 0 radians, like we're just starting at the beginning. And it comes to a rest. Ooh, rest. Maybe that's important. Rest. That would be final angular velocity. Okay. And the bake rub space. All right, cool beans. Find the angular acceleration of the wheel, assuming it to be constant. Now, we better get a negative. And so what I'd like, let's just talk about this real quick. You guys can see that it's spinning clockwise. All my engineering students, counterclockwise. Counterclockwise is positive. It's slowing down. Acceleration is going clockwise because it needs to be pushing against it. So it should end up being negative, which it will. Don't worry. Okay. So let's go ahead and do part A now. Find the angular acceleration. Okay. So we need angular acceleration. We have all those beautiful formulas on the front. So we need a formula that has angular acceleration in it. So we could maybe use this one. What don't we have? What's not given to us? We're not given anything to do with time, I don't believe. So how about this one? Why don't we use this angular velocity squared? Okay, I'm going to flip over the page. Maybe you want to write this down. I have it here. I did the problem already, so I can steal it from my example. So we're going to do ending angular velocity equals beginning, squared equals beginning angular velocity squared plus 2 times angular acceleration, which we'll solve for, times, how did I put it on here? Which one did I do? Oh, this one means change in theta. So you can do theta minus original theta or change in theta. I don't really care. You guys can do theta minus original theta or just understand this. That's like how much it moved, change in theta. Let's fill stuff in. Final velocity, because it stopped, is 0. Original velocity, 3.4, plus 2, angular acceleration unknown. Final position is 7.854 minus original position of 0. Take this, so here we go, ready? One step on our calculator. If you're not there yet, that's okay. Take your time. Do it in as many steps as you need. Just make sure you know how. 0 squared minus 3.4 squared. I'm going to divide by 2. And I'll also divide by 7.854 minus 0, which is nothing important. So here we go. Angular acceleration. Do that in as many steps as you need to, please. Negative 0.7359 radians per second squared. I love it. Is it negative? Yes. Is it slowing down? Yes. That's wonderful. Excellent. Part B. Part B says, how long? Okay, so no new information, just please solve for time. So let's get ourselves an equation that has time in it. So, I mean, we can just do the first one. There's nothing wrong with just using the first one. It's a nice, short, and sweet one. We can solve for time. Angular velocity equals original angular velocity plus acceleration, now that we have it, times time. Final velocity is 0. Original is 3.4. Angular acceleration is this number over here, negative 0.7359. I love this stuff. It's just so cool. We can do this in one step in our calc if we wanted to. We move here, boink, there we go. So we're going to subtract, so negative 3.4, we'll go to the other side, divide by negative 0.7319. There we go. So we end up with 4.620 seconds for a time. I didn't think about like Wheel of Fortune or something like that. That sounds about right. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. You know what I mean? Like, that sounds cool. I like it. All right, example 3. Let's do this thing. A pulley rotating counterclockwise, positive, in the direction is attached to a mass that is suspended to a string. Okay. The mass causes the pulley's angular velocity to decrease. By the way, that means that we have negative acceleration with a constant angular acceleration. Oh, and there it is, negative 2.1 radians per second squared. Slowing down, negative acceleration, just like linear. If the pulley's initial velocity is 5.4 radians per second, how long does it take? So part A, ready everybody? Oh, so given in the problem, angular acceleration, negative 2.1. And you can write the units on it if you want. Now we're going to move to part A. If the pulley's initial angular velocity, WO, I shouldn't say W, but I don't care, is 5.4 radians per second, how long does it take for the pulley to come to rest? Do you see how I did all that? Like, read it, write it, read it, write it, read it, write it, read it. Okay, stop Amy. So let's find an equation where it has acceleration, an original velocity, and an ending velocity. If I could encourage you, like if we were in class, I'd be like, okay guys, somebody find me a formula, and I would just sit there at the board. Oh look, food from yesterday. You think I would be embarrassed by that, but I'm not. Okay, I'm gonna use the first one, angular velocity. I think we have everything we need here. Let's plug everything in. So come to rest, 0. And original, 5.4. Angular acceleration, negative 2.1. And time is unknown. Let's grab our calculator. Put it over the mess from our food yesterday. And we got Vesuvio's delivery for Mother's Day. It was very nice. Negative 5.4 divided by negative 2.1. Oh, if anybody cares, I know you all care. We're getting our bathroom fixed, both of them. I will not tell you how much money it costs. Let's just say that we're trying to do our part in helping the economy. All right, so I got 2.571 for my time. Sounds good. And let's go ahead and look at part B. Through what angle, okay, so that's theta, does the pulley turn during this time? So it's pretty much asking how many times does it spin around. Okay, let's go ahead and figure that out. Let's see how many times it spins around. So I need to solve for theta. Okay, if they say angle or revolutions, you got to solve for theta. Oh, I have them right here. I don't need to flip back. I would love it if you guys would pick your own and just see if you can get it. The final answer is, let's see, 6.94. So let's see if Miss Angela can pick a good formula. Does not matter. On my example, I did this one. I did theta equals angular velocity original time plus 1/2. This is what I used, which was, oh, if you're like Miss Angela, that's not a real formula. That's because I didn't acknowledge the fact here. I just negated the fact that, there you go. The original position was 0. So when I wrote my originally, I just got rid of this term, just goes away. All right, so final position is theta. Original position we'll assume to be 0. Original angular velocity of 5.4. Time we just got. 1/2 is always 1/2. Acceleration is negative 2.1. And time is what we just got. I love how it's like you could literally pick any of these equations and they all just come together. Oh, and look, this is a simple put in your calculator. Let's do it. What do we get? 6.943. And, oh, I must wrote seconds. This isn't time. We're solving for theta. So remember, theta is measured in, can you finish my sentence? Theta is measured in radians. So like, this is a good answer, but if we want the angle, you can simply, so that's radians. Let's think about this, Amy. If I wanted to know how many revolutions it was, I would divide by 2 pi. So I could just do 6.943. Make sure this is right, Amy. You would divide by 2 pi. Is this right? Okay, ready? You're going to see, ready? Here's your math teacher's brain at work. If 1 revolution is equal to 2 pi radians, and that equals x revolutions out of 6.943 radians. I just want to know how many revolutions it is. It doesn't ask for this. I feel like this is something good to know. Cross multiply. And so I would, yes, divide by 2 pi. So I could say that it rotated 1.105 times. And if I really wanted to, then I could just multiply by 360. So how many degrees did it spin? It spun 397.8 degrees. So like one full circle and just a little bit more. One full circle and look. I like seeing those things come together. So if you're wondering why I bothered to solve for that, I think it's nice to be able to wrap our heads around what like a radian is and all that stuff, okay? All right, let's do this. You have finished watching a movie this is neat, on a Blu-ray, and the disc is slowing to a stop. Ooh, stop means angular velocity at the end is 0. The disc's angular velocity at the beginning of the problem, so this original, that's the original angular velocity. And its angular acceleration, look, they are giving us so much, I love this, is -10. This line PQ is on the positive x-axis. Okay, cool. So they're just saying like it's here at the beginning at t equals 0. What is the angular velocity at this time? And what angle does PQ make with the positive x? Oh, this is such a neat question. I love it. I think you guys are going to like it too. All right, so let's write some givens. Okay, so first thing I know is that it's going to go to a stop. The second thing they told me is the original is 27.5. Do you love how Mr. McBurney actually gave us like room to work? Yay! Now, do not write time equals 0, please. They're just, all this meant is at the beginning of the problem. They're not saying in 0 seconds is the end of my problem, all right? And it's angular acceleration. I'm getting a little better at those. I try to like draw a straight line from my A and then I make an A. Is -10. I made fun of Mr. McBurney's fish, but really mine looks like a fish too, so who am I? And now for part A. Part A adds the fact that time is 0.3 seconds, so very, very, very short. You can add all those zeros if you want to. I'm not going to. And they want us to know, what is its velocity at this time? What is the disk's angular velocity? Okay. So we're not actually going to let it come to a stop, part A says. Part A does not say, part A does not care about like the final part of being 0. Part A just wants to know like it's spinning really fast, and they're saying what is the velocity at 0.3 seconds. So it's not actually going to be 0. So this, you know what, I feel like that's there maybe to trick us. So what is the angular velocity at this time? It is not 0. It has not stopped yet, unless we get 0. Okay, some really cool formulas. Let's go ahead and figure out which one we're going to use. I would appreciate you pausing the video and trying to figure this one out. The answer is 24.5. All right, maybe you paused the video, maybe you didn't. I am going to use anything I can. I'm not even going to hear. I'm getting rid of this because they're just saying it's going to come to a rest. Part A doesn't really care that it becomes to a rest. So I'm going to do angular velocity equals original velocity, acceleration times time. So this is my angular velocity at 3 seconds equals my original 27.5. It is accelerating at a -10 acceleration, and the time, we want to know how fast is it going at 0.3 seconds. This is a very simple plug and chug. Oh, Eponine, are you thinking about Aaron? I got 24.5. And this is angular velocity, so this is radians per second. And now let's take a look at part B. What angle, theta, does the line PQ make with the positive x-axis? Well, let's solve for theta first. We have lots of fun equations to solve for theta. Why don't we pick, I don't know, pause the video and pick one. You need to be able to get 7.8 radians. It really doesn't matter as long as you solve for theta. Let's see, I think I have a ton of stuff here. I'll just do this one. I'll do theta equals original theta, angular velocity. There we go. I'm going to use that one and solve for theta. Okay? So I don't know what theta is. It was originally at 0. My ending velocity is 24.5. My time is 0.3. Minus 1/2 is 1/2. Angular acceleration is -10. I love all this space. And time squared. This is a simple plug and chug into our calculator. Let's do that. And I got 7.8, which is exactly what we should get. Now, this is not 7.8 degrees. This is 7.8 radians. So you can do this however you want to. But here's what I want you to understand. I like to divide this by 2 pi. Because if I divide it by 2 pi, that tells me how many revolutions it makes. Okay? This is just how my mind goes about it. Okay, so if I divide by 2 pi, I end up with 1.241. 1.241 revolutions. So if you need to go even further, you take that and you multiply it by 360. That's 446.9 degrees. 46.9 degrees. So all of these are very helpful for the final answer. So here's what I want you to understand. This was our disk when we took it out. Line PQ was right here. Okay? It did 1 full revolution and 0.241 more. So the question is, I now have my line at, here's the x-axis, right? My line is somewhere here. PQ. Because it went around a whole turn and a little bit more. So it went around a whole turn and a little bit more. How much more? 446.9. Here's how I do this. I said, well, it's 446.9 minus the whole turn of 360 is 86.9 more degrees. So it had to go 360 degrees for the 1 turn. So that was 1.241 plus it had to go this extra 86.9. Okay? So when it says, what is the new angle from the positive x-axis, I would dare say it's 86.9 degrees. Pretty darn cool if you ask me. I mean, I guess if you answered 446.9 degrees from that, it would also be correct. Okay, and honestly, Mr. McBurney ended at 7.8. I just wanted to wrap my head around it a little bit more, so that's what I was trying to explain. I hope you guys enjoyed 10.2. Who knows how far we'll, my gosh, don't look how dirty my table is. Who knows how far we'll get. Maybe we'll find some cool problems or videos online, take a break from the notes. But I hope you guys have a wonderful day, and I am missing you like crazy.